But let's look at a similar case, but this time done from the perspective of negative correlation. Okay, so let's look at it from the perspective of negative correlation. Okay, so negative correlation would look something like this. So this would be X, this would be my maths paper, and this would be Y, this would be my stats paper. Okay, so in other words, negative correlation will look something like this. Okay, so again, if I draw in my mean mark of my maths, and if I draw in my mean mark of my stats, okay, then the majority of my data, let me just draw a little bit nicer. The majority of my data lies in either this quadrant, or this quadrant down here. So it lies in the alternate two quadrants for negatively correlated data. So if I lie in either of these two quadrants, then that means, well, let's have a look at it, okay? It means, for example, this quadrant up here, that I'm below average on the maths. Okay, so I'm below average on the maths. In other words, xi minus x bar is negative. But I'm above average on the stats. Okay, I'm above average on the stats, which means that yi minus y bar has got to be positive. So one option that I can have is that xi minus x bar is negative, so I'm below average on maths, but I'm above average on stats. So that's positive, okay? Or the other option would be in the other quadrant, okay? So down here means that I'm above average on maths, okay? So that would simply mean that xi minus x bar is positive, so I'm above average. And I'm below average on the stats, okay? So I'm below average on the stats. In other words, yi minus y bar is below average, it's negative, okay? So yi minus y bar is negative. So these are the two options that I can have. They kind of do opposite things, okay? So either I'm above average on maths and below average on stats, or I'm above average on stats and below average on maths, okay? So let's have a look now at what happens if I multiply these two quantities together. So if I multiply these two quantities together, have a look at this option. This option here says that I'm below average on maths but above average on stats. So I'm taking a negative value and I'm multiplying it with a positive value. That's negative, right? Now let's also have a look at the alternative situation, which is above average on maths and below average on stats. That means that I'm taking a positive value and timesing it by a negative value. That's also negative. So I can literally say that for negative correlation, this quantity, in other words, the difference between the values and their respective means in both the maths and the stats papers, should be negative. So let's summarize that, okay? Now actually, this quantity here, this xi minus x bar times by yi minus y bar, looks like something that we have kind of talked briefly about before. It looks like something called, well, it kind of follows the same form as standard deviation, right? It kind of follows the same form as variance, okay? So it means that if I add it together and take the average of it, okay, remember I haven't taken the square root yet, okay? This is gonna be the covariance, okay? This is gonna be the covariance. Now I said that I haven't taken the square root yet, okay? So literally I followed the same kind of principle as standard deviation. I said, well, look, I look at this quantity here, this looks something like I've met before, okay? If I take the mean of all those values, then that should give me the covariance. Now I said that I haven't yet taken the square root, but in actual fact, there's no such thing as a co-standard deviation because I can't take the square root sometimes. Have a look. If I have this situation, I'm allowing my values to be negative, okay? So I'm allowing my values to be negative, right? So if I'm trying to take the square root of a negative number, that doesn't result in a real number, okay? So actually, there's no such thing as co-standard deviation because this thing I'm allowing to be negative. Okay, I'm not going to square it or anything like that because, of course, I want to know whether it's positively correlated or negatively correlated. It is useful to keep the positive and negative in this case, okay? So let me just summarize here, okay? For positive correlation, I have seen, for positive correlation, so something like this. So for positive correlation, the covariance of my two random variables, okay, should also be positive. So remember, my covariance is given by this thing here. Whereas for negative correlation, I'm literally saying something like this. I'm literally saying my data looks something like this, then in that case, then my covariance has got to be negative. Okay, so this is quite nice. The covariance literally tells me which of the two quadrants I lie in. Okay, so which of the two quadrants I lie in? Do I lie mostly in this quadrant and this quadrant, or do I lie mostly in this quadrant and this quadrant? Okay, and the covariance will tell me which two quadrants my data will lie in, just simply by multiplying those two differences in the means together. Okay. Now what I want to do is try and put it all together to understand the strength of the correlation. So let's just have a look. Let's just take the case of positive correlation first of all. If I have values that kind of look like this, it's still positive correlation, right? But it's quite spread out, okay? So it's quite spread out. So in other words, if I look at the standard deviation in both my X and my Y values, so my maths and my stat score, they should both be quite big, okay? So sigma X and sigma Y should be large, okay? So what type of correlation would this be? How would you describe this? Well, this correlation would be quite weak correlation, right? So I'm saying for weak correlation, both the sigma X, so the standard deviation in my math score, and the standard deviation in my stat score, so sigma Y, should be quite large. Both of those values should be quite large. Whereas for stronger correlation, so something that looks like this, say, all right? When I look at my sigma X and sigma Y, so this is for strong correlation, when I look at sigma X and sigma Y, okay, those standard deviations should be much, much smaller because look, I'm looking at the average distance, so the average distance from those mean marks, okay? And if that average distance is generally quite small because the data is quite well behaved, so the spread is quite small, okay, then sigma X and sigma Y should be quite small, okay, should be small. So this is a really important and fundamental idea, okay? I have this up here. I have the idea that covariance tells me whether my data is positively correlated or negatively correlated, okay? But then I also have the idea that the standard deviation tells me how strong or weak my correlation is going to be. So I have this idea, okay? For strong correlation, okay, my standard deviation is going to be quite small, okay? And in actual fact, it's going to be very, very similar to the covariance of X and Y, right? For weaker correlation, my standard deviation should be much, much larger. So what I'm going to try and do is put this together. I'm going to try and put these ideas of covariance together and also standard deviation together and compare them so I can get some meaningful understanding of what's happening with my correlation. So R, and the reason why I call it R, is it's just simply a comparison or a ratio of my covariance, so my covariance, to my sigma X and my sigma Y. Okay. Now just remember, covariance is just simply a product of my differences and my means. So it makes sense that when I'm comparing it to my standard deviation, I should also multiply those standard deviations together because again, those are differences from the means. Okay. So I can say in general then that R, and the reason why I call it R again is because it's a ratio of my covariance to the product of my standard deviations. That's all it is. That's all R tells me. It's just simply a ratio of those two things. Now clearly this now makes sense because for weak correlation, sigma X and sigma Y should be quite large, okay? Which means that I'm dividing by a large value because I'm timesing sigma X and sigma Y together. So for weak correlation, okay, sigma X and sigma Y is large. So therefore, I'm dividing by a large number, which means that R should be close to 0. Because if I take something and divide it into lots and lots of equal parts, each part is quite small. That's exactly what I want. For weak correlation, I want R to be small. It wants to be close to 0. That's literally what we said right at the very beginning. Whereas for stronger correlation, stuff like this, then I can say that actually sigma X and sigma Y, so for strong correlation, okay, sigma X and sigma Y looks approximately like the covariance because literally the covariance is just the product of those distances, just like sigma X and sigma Y is a product of those distances. So for strong correlation, those two things should be roughly the same, which means that when I divide them by each other, when I divide them by each other, I'm basically dividing the same number by each other. So in other words, R should approach 1 or negative 1. Okay, because of course covariance could be negative. Okay, so again, this is exactly what I want. Strong correlation goes to 1 or negative 1. So it's beautiful. It makes sense that it should be a ratio of these two things. It tells you a lot of information here, compressing a lot of ideas just simply by dividing. Now let's just fill it in then. So rather than writing covariance as sigma x and sigma y, let's actually replace it with what we know. So I know that the covariance is 1 over n times by sigma xi minus x bar times by yi minus y bar, right? Then I'm going to divide that by the product of the standard deviations. So standard deviation of x is going to be sigma, a square root of 1 over sigma xi minus x bar all squared. We've already looked at that. And then the standard deviation of y is just going to be the square root of 1 over n times by sigma yi minus y bar all squared. Okay? Now I guess we can do just a little bit of tidying up here. You notice that I've got the product of two square roots on the denominator. So I can really easily and quickly just write that as one big square root because it's just the product of two separate square roots. You notice as well that I've got 1 over n times by 1 over n. Okay, so therefore I can rewrite that as 1 over n squared. Right, you happy with that? And therefore, because I've got the square root again of two things being multiplied together, I could, if I wanted to, rewrite that like this, because it's the product of two separate square roots. The reason why I wanted to do that is because have a look at the square root of 1 over n squared. Just square at the top, square at the bottom, that becomes 1 over n. The reason why I wanted to do that is because look, 1 over n and 1 over n just cancel, which means that effectively I'm just left with this. And I guess if I wanted to, I could always just tidy that up slightly and have a look. I recognise some of these formulas. Okay, I recognise some of these formulas. So have a look. This thing here, you should recognise is just sxy. We've already done a video on that. You should recognise this thing here is just sxx. And you should also recognise that this thing here is just syy. So in other words, how I can rewrite R is it's literally just the ratio of the covariance to the standard deviations. That's fine, okay? But how I can also rewrite R is it's sxy divided by the square root of sxx divided by syy. So this is an equivalent formula for the correlation coefficient, but don't lose track of what's going on in the background. Okay, the covariance tells us whether it's positive or negatively correlated. Okay, so that's what the covariance tells us. And then the standard deviations tell us the average spread in the data in each of the two directions. So if the standard deviation is large, it means it's weak. And if the standard deviation is small, it means it's strong correlation. And I can do that, I can put all that together by taking the ratio. So it's a really lovely little way of understanding. It's really, really clever. I think it's amazing, right? Just simply by thinking about the ratio of the covariance to the standard deviations in the x and the y direction, we get an understanding of what's going on with the correlation.